Good afternoon. I'm Bob Zimmer. I'm president of the University of Chicago, and it's really a great pleasure to be here at this particular moment and to welcome all of you here. This is a seminal moment for our computer science department. This building has been, I would say, something like it has been desired for quite some time. It's now here and open, and that's a great thing. But I think it's also important to think about this building in a larger context, namely that this building is really one piece of what we intend to be a large sequence of investments in computer science, a large expansion of the computer science department itself, a large expansion of things connected to computer science around the university, connected to data science. So the way to think about this building is that it's a necessary but not sufficient piece of what it is that we actually want to do as a whole in computer science. So you can see by our guest speakers' talk that there's a lot to say and a lot to think about the whole evolution of the field. It's been quite remarkable, and I think we're all confident that the future is going to be likewise remarkable and not entirely predictable, except that it will be remarkable. Exactly how it will be remarkable remains to be seen. But I just want to thank all of you. I think I see Bob Soar here, and I want to recognize him. And Bob was really the founder of this department. As many of you know, it grew out of the mathematics department, since we at the time had no engineering, and which was, of course, the locus for most computer science departments in terms of their origin. So I just want to recognize and thank Bob for everything he did to create this department and set up. Today wouldn't be here without Bob's work, so thank you, Bob. All right, so again, I just want to offer my congratulations and hopes and expectations for everything great that's going to happen in this building, and I'm looking forward to the moment when the building's too small, because the activities in computer science have grown so much and so robustly that we'll have another problem of figuring out what it is we have to do next in terms of space.
I'll give you about a year.
A year, okay. All right. Now, I see our provost has arrived, and so I'm going to turn the floor over to him. But thank you to all of you for building and making this department great now, but yet greater in the future. So thanks very much, Daniel.
Thank you, Bob, and let me add my own words of congratulations to all of you. I had an opportunity to look a little bit around in the building, but it's certainly a magnificent space and I think a wonderful new home for the computer science department. As Bob has mentioned, growing the computer science department and thinking about what we as a university want to do in terms of like data analytics and collaborations with the statistics department, with the Department of Mathematics, the physical sciences division, but also more broadly university-wide across campus is one of the top priority for us at the university at this moment. We've went through the important steps of getting this right. The most important first thing is to get the right leader in place with Mike Franklin, and he'll say a few words in a minute. But then also it's very important that we are thinking about what we want to do. How do we want to make sure that this fits well with the University of Chicago? And then, of course, the most important part of that, or maybe one of the most important parts, is to have a space that encourages collaborations across the different areas, and to also be able to create new ways to engage with each other for new research activities, and then most importantly with other parts of the university. I couldn't be more excited to where we are right now. I think we have a wonderful approach. We brought new people to campus, and now we have a home where all of this can occur. So I want to all of you, thank you for coming. Again, congratulations on what is, I think, a magnificent space. And as Bob has said, hopefully our next problem is that we're going to grow out of space soon. Thank you very much, Mike.
Okay, great. So I'm Mike Franklin, Chair of Computer Science, and I also, I'm supposed to be an advisor to Daniel, but I don't know if he really listens to my advice, but I try. I think he does. Anyway, I just want to say quickly, you know, it's an amazing time to be a computer scientist and to be involved in computer science in general, but also particularly here at the University of Chicago, because things are really, really moving. We're in the midst of a huge expansion of our program across just about any dimension you can think of, and we've hired some amazing new faculty. Nearly 2/3 of our faculty have been here 7 years or less, which is kind of mind-boggling at a university department. And we're expanding into a huge range of new areas, artificial intelligence and machine learning, human-computer interaction, security, data science, quantum computing, and so on down the list. And more importantly, or maybe equally as importantly, we're collaborating across campus. So if you look across any modern university, everybody is changing the way they're thinking about the world because of all the data that they have available. The computational tools that are available to help make sense of that data are really allowing types of thought and types of discoveries that just couldn't have been done before. And the way that we're going to succeed at that as a university is by working together and collaborating across these different areas. So obviously the most visible sign of the momentum we have is this beautiful building that we have, or the renovation. And you'll see that a lot of thought has gone into it. We built a really modern environment that's really geared to encourage collaboration. There's a lot of open spaces, there's a lot of laboratory space, there's a lot of areas where people can just bump into each other. And if you hang around the building for a little bit, as I hope you do after the presentations, you'll see that the energy level in the building is just off the charts. You just see people everywhere. And the energy level will go up even further when we open the espresso bar downstairs, which will hopefully be in the near future. So we we invite you to explore the building after the talks. So I have a cheat sheet because there's just a huge number of people that deserve recognition for this effort of moving us here. So I'm going to name some names, and if I leave anybody out, I apologize. But you know, obviously, I want to thank the support of Bob Zimmer and Daniel Diermeier, you know, who really drove the project forward. They had the vision that the university needed to expand in this area, and they had the foresight and the guts to you know, make that a priority, marshal resources that needed to be marshaled, and to really help get the university campus behind the effort. And so really without that kind of leadership, we wouldn't be here today. So I'd just like to recognize them if we could. We've had tremendous support from the Physical Sciences Division, so Dean Angelo Linto is in the back. And and Rocky Kolb, who was previously dean, was a huge supporter and remains a huge supporter of computing and data on campus. Blair Ochambeau, Mike Hopkins in the Provost office, Stephen Meyer in the PSD, Brenda Johnson, who I noticed was here for head of the libraries, has been a great partner in this. And really the support of all the trustees and deans and officers, because it was a huge project and a huge change for the university, and so we really needed that kind of support. We had a working group of faculty. I just want to mention them because they really did work. Shan Liew, John Reppy, James Evans, Barbara Curran, also from the libraries, had meeting after meeting after meeting with the architects and the builders and the facilities people. And we got most of it right, not everything. We got a lot right. Jennifer Robles, project manager, who's around there, is tremendous. Hi, Jen. It's in the back. So let's thank Jen, because it was a huge project. It remains a huge project, and there's no way it would have gone as smoothly as it's gone without Jen paying the attention to it that she has, and being so patient with us and so easy to work with. So that's important. Carrie Galbraith, also from Capital Projects, has been running interference for us and making sure that we're happy. Laura Stewart, I want to call out. I don't know if Laura's here, but you might have noticed the beautiful art that we have from the Smart Museum. That was Laura, who not only picked out the pieces and where they were going to go, but actually did all of the necessary arm wrestling and cajoling to get the museum to loan us those pieces, because they don't usually do that anymore. So Laura's been a great partner there. And Jason Salavon, who's one of the artists that we're featuring, has also been really helpful there. Getting close to the end of that list, an amazing staff in computer science, administrative staff, and the technical staff. The move went about as smoothly as it possibly could have gone. We had a date, we hit that date. It was on a Friday. When we showed up Monday, just most things worked. And to the faculty and the students, it looked like magic, but it was only because there was so much work ahead of time to get it right. And then, when it happened, these people were working, around the clock through the weekend to make sure that everything worked. So I want to thank the administrative staff and the tech staff, and in particular, Bob Bartlett and Nita Yak, who are out there. So let's thank them. The students and the faculty have been great. Change is hard. We moved out of a building we had been in for 30 years, 40 years, I don't know. Everyone's been really positive about the move and really patient when hiccups arise. And so that's been great. And then just a quick shout out for this event. So Rob Mitchum, Melissa Bradford, and I want to do a special call out to Tom Dobes, who's wasn't really supposed to be our AV person, but he ended up basically reprogramming all our AV systems to get them to work the way we needed to. So just for all those people, thanks very much. All right, great. So now we're going to get started. Dave's like, come on, Mike, all right, let's go. So, all right, good. So Dave Patterson, first I got to thank him for making the trip out here. I have to say, I was excited, like a lot of people, to hear the announcement that Dave and John Hennessy were named the 2017 Turing Award winners, which of course was named this year. And I have to say, the first thing I did is I sent Dave a note of congratulations, which he very graciously responded to, given that his mailbox was probably overflowing. But then I kind of counted to 10, and then I sent him another message that said, hey, Dave, we're opening a new building, and it would be great if you would come out, and kind of help us kick off an event with, in real style by having this year's Turing Award winner. So he agreed to do that. He brought a huge contingent of Pattersons and other related people that he'll introduce you to. But thanks to all you for coming. So. Just quickly, so Dave's a professor emeritus. It's hard for me to say, but he is a professor emeritus at UC Berkeley. We spent a bunch of years together. 5 or 6 of those years we're actually sitting in the same cubicle in a big lab, and so we got to know each other pretty well. He's a distinguished engineer at Google, where he's working on the latest hardware to accelerate machine learning and AI, and he's going to talk about some of that work today. As you know, he's the 2017 winner of the ACM Turing Award, along with John Hennessy. And the award was giving, and I'm going to quote, it's for pioneering a systematic quantitative approach to the design and evaluation of computer architectures with enduring impact on the microprocessor industry. Now, that's pretty impressive. But what was amazing about when Dave won the Turing Award wasn't that he won it. We all knew it was going to happen eventually. But the next question was, well, what did he win it for? right? Because there were easily 3 or 4 contributions that he had made over his career that were Turing Award worthy. So he made seminal contributions to storage architectures, RAID and things like that. He made seminal contributions to large-scale systems architectures. Network of Workstations project is kind of a very early project that kind of shows us how large-scale computing gets done today. And a bunch of other really impactful projects that he worked on over the years. And not surprisingly, he's a member of the National Academy of Sciences, National Academy of Engineering, Silicon Valley Engineering Hall of Fame, it goes on. So I'll let him tell you the rest. But I just want to point out, beyond his research contributions, he's made a bunch of other really important contributions to computer science. In particular, as an educator, he's written some of the seminal books in computer architecture at many different levels. And he's created a number of classes that have been delivered to tens of thousands of students at Berkeley, usually per semester, and and have been adopted really around the world. He's also built a model of really collaborative, high-impact computer science research that many of us try to follow, and showed that you can do great intellectual work and also have impact on the real world, and that in fact, not only are those two things not opposed to each other, but they actually amplify each other. And he's shown that time after time. And then finally, I just want to call out the work he's done for the CS community. He was a president of the ACM, he was chair of the CRA, and he was very heavily involved and remains involved in diversity and inclusion issues through the Tapia Conference and Grace Hopper and other things like that. So with that, it's my great pleasure to introduce Dave Patterson.
All right. Well, thanks. I think we can just declare that the reserved seats are available. So you want to come on, the people in the back, come on up. Come on. Empty chairs make me nervous, so you should. So I'd like to thank the president and the provost for coming. In computer design, they adopted the word architecture. So I can call myself an architect. So as an architect, I approve of this building, Michael. So Mike and I, tried this experiment about trying to get people to work better together by redesigning space, and it worked really well. And Mike's, as far as I can tell, Mike's taken all those good ideas and applied them to this building. So I'm anxious to come back in a couple of years and see how it works. But it looks like it's going to be really fantastic. And that was a very, very generous introduction. So thanks. If you want to see Hannah C. give half of this talk, you can go to this website where we gave the Turing lecture. So one of the things I have to do, Mike won't be surprised, is brag about Berkeley while I'm here. So when I got the award, my friend at Stanford said, there's a remarkable thing that's happened here, it's where the Turing Award was done. So when you talk about Turing Awards, there's a lot of lists, and it's where are the people now, or where were they as students and stuff. Osherhout said, the question is, where was the research done? And if you use that measure, amazingly, 7 of the 51 Turing Awards were done at Berkeley, and 2 of them shared it. So when trying to figure out what to do about this idea, how do we get the word out, one of my former students said you should give a lecture series, and so that's when as an emeritus professor, I organized that. And we're halfway through. And Manuel Blum just talked on Thursday. And I did this kind of to brag a little bit, to show off about Berkeley. So how many is 7? So our big rivals at Berkeley are MIT and Stanford. So if you take Berkeley and you add MIT and Stanford, we have the same number of Turing Awards as those do. And so, but I've come to, and I've gone to these lectures. These are some of the best lectures I've ever seen, and many of them all of them are outside my area, but mine. And so I'd encourage you to go look for them and read them. We did 2 things. We did the lectures, and we also did a lunchtime interview with the people talking about their personal lives and how they did what they did, and advice to grad students and stuff. And I think they're all pretty interesting. So I'll stop bragging right there. Okay. So what I'm going to do is talk about, there's actually kind of 4 parts to the talk. I'm going to talk about the history of computer architecture. I'm going to give you a half a century of computer architecture in about 10 or 12 minutes, so get you up to speed. I'm going to talk about the challenges facing our field right now. There's some real big problems facing us, and then I'm going to talk about opportunities in the future. And then I'll do some questions and answering, and then I think I'll have enough time to do kind of a quick personal history and advice to be able to do that, and I'll introduce my family. Okay, so the lessons from the 50 years is software advances can inspire hardware advances. When you raise the hardware-software interface, that lets opportunities for computer architects. And in our field, we are tied with industry when we do computer design, and the way we settle debates isn't arguments and papers and stuff like that. People invest billions of dollars in our ideas and put them in the marketplace, and the marketplace figures out who was right and who was wrong. So I'll tell you that. So first of all, when we talk about architecture, there's the phrase instruction set architecture, and this will play a role throughout this. What is this? It's just when software talks to hardware, there's a vocabulary. And the words of this vocabulary are instructions. They're the commands the software gives the hardware. So those are instructions. And so what do we call the vocabulary? We call it an instruction set architecture, and I abbreviate ISA. Okay, so who cares about that? It's the most important interface in the computer. It's because it determines what software can run on that hardware. So that's what we're talking about, instruction set architecture. So if we go back 50 or more years to IBM, they had this big problem. They had 4 independent lines of computers with 4 different instruction sets, 4 different software stacks, and 4 different market niches and marketing terms. So that was bad because there was a lot of duplication. So IBM engineers had this idea at the time that they could invent a single one of these vocabularies, a single instruction set architecture that would work for all these marketplaces. So that was their goal. Now, to pull that off, it was going to be really hard. It's like 4 independent companies. And the big challenge in computer design today is not what's called the data path. It's kind of like the brawn, the thing that does the arithmetic and stuff like that. It's the control. It's the brain is the hard part, right? The brain of the electronic brain is the hard thing to design. So they went to the second person who won the Turing Award, Maurice Wilkes, a computing pioneer, and he had this idea how to simplify the design of the brain. He said, let's just specify it as a 2-dimensional array, with the columns being the control lines, and the words, he'd call that micro instructions. So it's kind of like software programming. It was inspired by software, and so what he called the micro instructions programming, he called it micro programming. So IBM decided we're going to bet on this idea to build a single instruction set for all these lines of computers, and they're going to bet the company, if this failed, the company would be in trouble. Bet the company this is going to work. So the biggest announcement in the history of IBM was April 1964, and here's an example of 4 different computers they announced on the same day. You can see it varies in the kind of the brawn, the data path by factors of 8, and the clock speeds by factors of 4, and then the price by factors of 5. So this is millions of dollars in today's dollars per machine. So IBM bet the company that this idea would work, and they won the bet. IBM dominated their field for decades, and even today, 55 years later, that business is a $10 billion a year business because of the decisions they make. And one of the people who led this design was Fred Brooks. He's another computer architect who won the Turing Award, and he was the leader of this project. Okay, so microprogramming and IBM. So now we move into the smaller computers, which are called mini computers, and they're built out of transistors and particularly integrated circuits. And so in this case, the way that they implemented those 2-dimensional arrays was a memory, and now the memory could go bigger because of Moore's law that we've heard about. Moore's law is more transistors per chip every year, double every year or 2. So with more transistors, we could have bigger control stores, so we could have bigger microprograms, so we could have more complicated instruction sets. And the shining example was this from a company called DEC, for the VAX mini computer. Now we get to the microprocessor industry. Now, the microprocessor industry, these people were good at building chips and manufacturing them, but they weren't good at computer design, so they just imitated what the big guys did. They just followed the same examples. So when they were going to do these vocabularies, they would say, well, look at this word that I've added, and here's how you would use it. And the other person, oh, I've got a better word. So it wasn't very scientific, and they were programming at this very low level. Amazingly enough, Gordon Moore of Moore's Law fame is a visionary, and he thought, this is in 1974, when they just had a so-called 8-bit microprocessor, varying with B microprocessor, that the next vocabulary they did, the next instructions that they did in 1974 would last the lifetime of a company. Whatever they did next, we're going to be stuck with forever. So what he did was hire a bunch of new PhDs in computer science, sent them from Silicon Valley to Portland, Oregon, to invent the next great instruction set. And this was eventually called the IAPX 432. It was by far the most ambitious project of the 1970s. It'd even be ambitious today. It started in 1975. Unfortunately, and they did a bunch of things, and they went from an 8-bit computer to 32-bit. It had a custom operating system written in Ada, all kinds of things. So very ambitious, but also some real performance problems and very late. So they had to go back to Gordon Moore and say, you sent us up here to invent the future. It's not going to be ready on time. So Gordon Moore and Intel had to start an emergency project because they needed a 16-bit computer in the marketplace, and it wasn't going to be done in time. And this was called the 8086. They gave the team with this mission, this emergency replacement mission, 52 weeks to do everything. Invent an instruction set, build the software, build chips, and get the bugs out and make them work. So 52 weeks are remarkable. So how much time did they have for the vocabulary, this instruction set? They had 3 weeks. They spent 3 weeks. 3 people spent 3 weeks on the instruction set, and then they moved to doing chip design. So it was announced to not a lot of fanfare. They had one, but it was no big deal. To Intel's tremendous fortune, around the same time, IBM decided to get into the personal computer marketplace to compete with Apple around the Apple II. And they needed a microprocessor. They needed a 16-bit microprocessor. They really liked the Motorola 68000 because it had a kind of an elegant instruction set architecture like the IBM 360, but it was late. So they picked the Intel architecture for this design. But you know, it wasn't going to be that big a deal because they estimated that over 5 years they'd sell 250,000, which isn't that many chips. But they were wrong. They got that completely wrong. It was 100 million. So this emergency replacement project fell into the lap of the IBM PC that became this incredible overnight success. So suddenly the 86 was important because the software for PCs that shipped as instructions was in the instructions that Intel owned. So suddenly the 8086 had this incredibly bright future. Now we start looking at these machines that have this micro-coded interpreters in them and how well are they working. So this is John Koch, another Turing Award winner at IBM. He noticed that what had happened is that we raised the level of programming. Instead of programming this very low level assembly language, we were doing all of our programming in a high level language. The test case for that is, could you write an operating system in a high-level language? And the Unix operating system, which was written in a high-level language, said you could do that. So if you do operating systems, you can do everything. So now what mattered is not what some clever programmer could do. What mattered is the compiler, something that translates from the high-level language into the low-level language. What does the compiler do with these instructions? So he had this idea, because he was building compilers as well as mini computers, and he said, let's use our compilers with this IBM mainframe instruction set, but let's only use the simple instructions. What'll happen if we only use the simple ones and don't use the complicated ones? It went up to 3 times faster. So by leaving words out of the vocabulary and only using a subset of the simple ones, it went better. And then at DEC, which built this mini computer, the people found that it took a lot of clock cycles, much longer than they thought, to execute this average instructions. But they found a lot of the microcode is not used. 20% of these words in this vocabulary were most of the space of the microcode and almost never executed. So that kind of calls into question this idea. So now we talk about going from complex instruction set computers to reduced instruction set computers. So the first idea is this memory that was the control store that used to have these interpreters in it. Let's throw that away and just turn it into a cache. And what a cache is just a small memory buffer that has recently executed instructions because they're probably going to be used again in the future. And so this meant that fast memory would change depending on what program was run. It was a really simple instruction set, so it didn't need The microcoded interpreter, as simple as microinstructions. It made it possible to do pipelining. Pipelining is like the way to build cars, where you do it at each stage, and so you can make the throughput of the cars or instructions go faster by pipelining. And the complicated instructions weren't used that often anyways. And then there was a software breakthrough done by people at IBM that made this simpler architecture work better by using the registers better. Okay, so that's a transition. So this is when Berkeley and Stanford come to the scene. As an assistant professor, I led a series of courses where we built chips in the class in a series, and this is the first one. RISC-1 was the first one, RISC chip. The following year, we did a much more efficient one, and this is also when John Hennessy and his team at Stanford did another one, the MIPS architecture. So there was this remarkable moment in time, I can still remember at the main conference where you present chips, where the Berkeley students and the Stanford students got up and presented their designs, their microprocessors, and when after they presented, there was a murmur in this giant audience with 1,000 people in it, and it was amazing that a handful of students, grad students at Berkeley or Stanford, could build a microprocessor that was arguably better than what industry could build. And so trying to explain this again, so what is induced executor? It's this vocabulary of simple words. And what the question was, wouldn't you have to read more of the simple words? And you would. You'd have to read about 25% more. But you could read them a lot faster. Like, how much faster? It looked like about 5 times faster. So the net effect was about a factor of 4 times faster. So RISC-1 over CISC. That's kind of informally saying it. There's actually a formula that we used, and the first one is the instructions. You need 25% more of those, but the clock cycles per instruction to be about 5 times fewer, so that was the win. And so formulas like this were not in the textbooks at that time. It was more like a Sears catalog kind of. So here's a computer, it has these features, here's the next page. So it was pretty unsatisfying. So John and I wanted to write a book, and so we wrote one, and I think it might even be, this might be this first book that came out that we did in 1989 might be the first one to have these formulas, but was filled with formulas. Even the inside cover has a bunch. So we wanted to make it more like a physics book and had this more quantitative approach to doing that design. Okay, so what happened, wrapping up our history here, what happened with CISC versus RISC? Well, Intel, a great engineering company, didn't take this lying down. What they did is, amazingly enough, is take these complicated instructions and translate them in hardware in real time into RISC instructions on the fly. So they had extra hardware to do that. And then they had RISC instructions internally, and any good ideas the RISC people had, they had. And they had much better semiconductor technology, much bigger design teams, so they could overcome that disadvantaged instruction set with better hardware. They also had, because the PC industry lowered prices, the margins were lower, so their computers were very attractive. And so in the peak, they were able to sell 350 million of these a year, and they eventually dominated not only the desktop, but the small server side of things. So that's the PC era. Post-PC era, starting with, say, the iPhone in 2007, now things are different. Now these companies are designing their own chips. They're called a system on a chip. Not buying chips from companies like Intel. So they want designs they can integrate in their chips, so-called IP. So what they care about is die area. So they didn't want that extra overhead of the translation, and they couldn't afford the extra energy costs of that. So these ideas of a simpler architecture and a simpler chip came more attractive. So there are now more than 20 billion chips last year were shipped with 64 and 32-bit processors in it. And 99% of those are RISC today. So this was, the marketplace settling that debate. So my version of it is the good guys won in the end, but Intel might have a different version of it. Okay, so that's brought you up to date history. What are the problems facing us today? Shockingly, Moore's law is over. We are now in the post-Moore's law era. So it's shocking because people have been claiming, it's been around for 50 years, and people have been claiming in the past that Moore's law is over, but it's really over now. We're off by about a factor of 15 of where Morse should set it. He said originally doubling every year. It's now doubling every two years. He's changed it to 75, and we're off the doubling every 2 years by a lot. A lesser known observation that's kind of equally important is by this guy named Bob Denard. he observed that how could you keep putting more transistors on a chip? Wouldn't it burn up, right? And he said every time we shrink the size of the transistors, so we put more of them on the chip, we also lower the voltage. And so in a unit area, even though it has lots more transistors, it's about the same amount of power. And this was true for decades. And then starting around 2008, it stopped being true. The reason was, there's the voltage, you just start running out of atoms, and the voltage got so low that it started leaking current all the time. And so it was worse. If it got too low, it just didn't work right. So they had to stop doing that. And so what you see is the power per area starts going up and to the right, and we get limited by the power per chip rather than the transistors per chip. So the first figure of our textbook is, over the decades, it's on its 6th edition, showed how fast things are improving. And so in the RISC era, performance was doubling every year and a half. For those of you who weren't around then, we would throw computers away that are perfectly working computers because your friend's computer, which is newer, was like 2 or 3 times as fast, and you were jealous. And I don't want to use that one. We'll throw that one away. So these days, what's happened is, with the end of Dennard scaling, we had to switch from 1 processor per chip to many, and so that gave us some benefit. But then there's this observation called Amdahl's law, which says there's a law of diminishing return of how many processors you have in a chip. So that's slowed down to doubling every 6 years. And then most recently, the last year, doubling performance was only 3%. I mean, it was 3%, so doubling every 20 years. So, and so nobody throws away a laptop to it's so slow, right? You throw it, when it's broken, you throw it away. So you keep it, I don't know, 5 years. But programmers, my friends and programmers, are used to this era where they just sit in their chair and their programs get faster, right? They don't have to do anything. That era is, you're going to have to sit 20 years in your chair if you're waiting for it to go faster. So this is a big challenge, and had a long time used to, software could get bigger, more bloated, and it's okay. The hardware is going to make it run fast. That era is over. How about quantum computing to the rescue? There's a lot of talk about quantum computing, even in the newspapers all the time. So a lot of big companies are making big investments in this area, so they think it's promising. And from the research sides, the physics, the math, and the theory is really beautiful, really interesting and insightful. Now, but these are big, this is big science equipment. You know, if a truck goes by, it stops working. So this is, you're not going to have a quantum cell phone, right? This is going to be big, maybe in the cloud. And there was just a meeting that Mark Hill, one of a Berkeley alumnus, one of my former students, went as a computer architect. He's not a quantum expert. And he asked this question. Hey, are you going to have a so-called killer app? What's the killer app that in the next 10 years, given where quantum computing is going to be, that everybody's going to want to compute? And they couldn't come up with one. So it's probably at least 10 years away for quantum computing. So we're going to need to come up with something in the cloud in the next decade, before quantum computing can come to the rescue. And then there's another challenge that I've written in the paper is security. It's embarrassing for those of us in the field how bad security is. There are these attacks now, not on the software, but on the hardware itself that's based on timing. So that's shocking to computer architects because we thought timing didn't matter. We thought as long as it executes correctly, you don't care how fast it runs. But by knowing how fast it is, you can reverse engineer and figure out information. So we need to reinvent computer architecture that will protect information from timing attacks, and that's a wide open problem. Okay, so Moore's law is over, Dennard scaling is over, performance isn't getting better, and security sucks. So that looks pretty bad. So we go to John Gardner, the guy who gave us Medicare as a member of the cabinet in 1930. His version was, what we have before us is breathtaking opportunities disguised as insoluble problems, okay? So now, breathtaking opportunities. So we see, John and I see the world this way. We see a software-centric approach, modern programming languages, which are really very productive, are also very inefficient on the hardware. Can we work on that? The other thing is, I think most computer architects agree with this, is we don't have any, we can't, general purpose computing is not going to go any faster. You're going to have to wait 20 years. Multi-core is limited by Amdahl's law. The only idea we have left is domain-specific architectures. The only idea we have left is attack a single domain, do that really well, but you don't have to do everything. And then you could actually kind of do both, this idea of having these higher level languages and do architectures for them and raising the level of abstraction. How slow are these languages like Python? Okay, this is from a colleague at Wisconsin, Charles Licence at MIT. So what he did was he took a pretty simple Python program, matrix multiply, and made it better. So going from Python to C is 50x. 50x. How much hardware generations is 50x, right? So as John said, he used to work in compiler technology, and for languages like C and C++, if you could make it go twice as fast, you're a hero, right? There's an opportunity of 50 to make it just go as fast as C. How about taking advantage of the fact that there's multiple processors? How much more faster could you go? Another 7x. Okay, now I mentioned about caches, these small memories. It's really important to lay things out carefully in caches. How much faster you could go? Another 20. Right? And then there are these special purpose instructions that can actually calculate a lot of things at the same time called SIMD that can do 16 operations at once. You can get another 9x. So when you multiply all that together, what do you get? 63,000 times faster. So if you do it naively in the really productive thing, Python, versus the fastest you could do it on a modern microprocessor, you're giving up a factor of 63,000. So as John and I say, look, we're here to point out there's opportunities here. If you're interested in the hardware-software interface, there's potentially you can make things go thousands of times faster. There's Turing Awards waiting to be picked up, right? Sitting right here on the floor, just work on this thing. You make Python go 1,000 times faster, you'll be a hero. And that opportunity absolutely exists. There's kind of 4 generations of RISC projects that I worked on in the 80s. Some of them tried to worry about having a little bit of architecture support for these fancy languages. Maybe it's time to look at that again, look at the compilers. People ask me when I give this talk, why aren't people working on this? I don't know. If I was young, I'd be working on a problem like this. Okay, that's the software. Now, domain-specific architectures. It's working on, you pick a domain and you build an architecture for it. And it's still software there. It's not like a chip that only runs one thing. It's just a narrower domain. So why would it work? So John and I did this book about it's not, we should be explaining quantitatively why it works. It's basically, the first one is that the more effective parallelism for domain. So-called SIMD, kind of like those instructions that I talked about, that's more efficient. It's more restrictive, but it's more efficient than the classical multiprocessor one. So it's more energy efficient, that counts a lot. Similarly, very long instruction words, the idea of big wide instructions versus the classical speculative out of order, that's more efficient. It's more restrictive, but it's more efficient. So since it only has to work in this domain, you can figure out the more efficient things. So those things, if they work better. They tended not to work as well for general purpose computing, but we don't care about that. The memory bandwidth I talk about, these cache ideas are great. They're guessing what you want, but when they guess wrong, they're really terrible. If you know the domain, the software can do it better than caches. And then, we don't need this big of numbers there to compute on. We've got special formats that are much narrower than the classic standards and maybe even small integers. So these ideas, when you use the more restricted ones, more efficient ones, can lead to big wins. Okay, what field, and then how do you map software to it, these domain-specific languages that are being invented to help programmers also raise that abstraction to help you map it to it? Okay, what field should we try and accelerate? Here's a field that's growing faster than Moore's law, right? Number of papers per year faster than Moore's law. So, and all of us in computer science know what field this is, right? This is machine learning, right? So if you wanted to keep up, every day, in January, every day you had to read 50 papers a day. These are papers going on an archive in machine learning. 50 papers a day to keep up. Okay. So at Google, they saw this coming and decided they needed to build some hardware. So this is what's called the Tensor Processing Unit, or TPU Volume 1. Our Andrew Chen, who's here, with the cover of his magazine that he's editor, last month's cover issue was on the TPU. If you use Google, it's been in production since 2015. If you use Google, you're using the TPU. It's helping you. for queries and neural machines, machine translation. Machine translation, it helped with the triumph of AlphaGo over the human Go champion. It was used for all those things. That was announced. They built it and deployed it in 2015. They announced it in May of 2016. What is it? What's in there? The key thing that's in there is this matrix multiply unit in the beginning, which has a remarkable 64,000 multiply units on it. How much is that? That's like 100 times more than it's in CPUs today and 25 times more. So how could they do that? Because it's domain specific. They throw out the stuff they don't need and put the resources onto things that matters. So even with a slow clock rate, if you do 65,000 of them every clock cycle, that's 90 terops, which is an amazing number for a 2015 chip. How much faster is it than the CPU and GPU? The figure of merit that's interesting is performance per watt, because we're limited by power than the Nard scaling thing. And so it's like 80 times better than CPUs and 30 times better than GPUs. But the way we measured that for that paper was production applications, which is a good way to do it. But Google doesn't share its production applications with anything else. So how are we going to do benchmarks? So I've been involved in an effort that's called ML-Spec. No, ML-Perf is the name. It's kind of, if you know what spec is, it's like spec for machine learning. This is, it's at least 23 companies. All the big companies you know about are participating. A lot of universities are involved. And the first deadline is 3 weeks from today. And so we're going to see all these highly competitive companies submitting their results for the first time using a fair set of benchmark suites. And probably the deadline is 3 weeks from today for the submission. And I think we'll take a few weeks to everybody agree that the results are valid, and then they'll go public. And so in about 6 weeks from today, that's going to be a big deal. We're going to see just how fast all these competing ideas are relative to each other. So this is what Google announced in 2016, built in 2015. 2017, they announced this successor that's TensorFlow version 2. And it's got, that's a board with 4 chips on it. And there's 256 chips in this thing. It's 11.5 petaflops. That's a lot of zeros. And then the next year, they built the following one. And this one is liquid cooled, so it's running even hotter. And they have a lot more chips. And the peak performance is 100 petaflops. What does this mean? What do numbers like that mean? There's a supercomputer list that's doing double precision floating point. And the number 4 computer on that list is 100 petaflops. So Google's not building one of these, right? They're building a lot of these. And so by that measure, it's going to be number 4 through N are going to be these supercomputers designed to run machine learning algorithms. You're kind of programming in this TensorFlow stuff, so very rapid advance. So from a computer architecture perspective, this is kind of a Cambrian explosion of architectures out there all competing. Google's betting on kind of one core chip, these really big, powerful multipliers and software-controlled memory. NVIDIA, who's kind of the reigning champion for machine learning, has lots of these cores and lots of threads and registers. Microsoft is using FPGAs to do customizing. So 3 very different bets by these 3 big companies. Intel's betting on everything. They decided to buy the company that FPGA was doing. They bought a bunch of companies that were doing things like Google is doing, and startup. And there's, besides all that, all this big company investment, there's 45 startups that are working in this place. A few years ago, those of us in hardware were jealous of our software colleagues who could do startups and wish there'd be startups in the hardware area. That problem is solved. And then with this new ML-Perf thing, everybody gets to play, right? We won't just go, well, what should I do? You should buy GPUs. That's conventional wisdom. We'll find out what you should buy when we do this. And and I don't know which of these is going to win, but I'm pretty sure the marketplace is going to sort this out. Okay, that's opportunity number 1. Opportunity number 2 is there's this idea called open source software, which everybody's heard about. How come we don't have that for these vocabularies, for instruction sets? So I'll tell you that story. So there's something that's called RISC-V. It's called RISC-V because there were kind of 4 RISC projects at Berkeley in the 1980s, and I told them that story, and the faculty member leading this thought, well, we'll call this one RISC-V. So it was time for us to pick a vocabulary to use for our own research. And the obvious choices were the Intel architecture and one a RISC architecture from ARM. But they were actually pretty complicated, and even if we wanted to, the companies barred us from using them. They were owned, they were unavailable to academics. So we started to do a project, a so-called 3-month project to design our own. It was led by my colleague, Professor Krista Sanovich, and star grad students. Andrew Waterman and Jensep Lee did the work, and then I helped out I provided the wisdom to the project. It took them 4 years, but they built a bunch of chips along the way. And then we had this thing happen. Those of us in academia are used to people complaining about what we teach. That just happens all the time. But the complaints were new categories. How come in your course in the fall you changed, and in the spring you changed the instruction set from how you use in the fall? Well, why do you care what we do with our internal instruction set in our courses? You know, what's the problem? And we realized there was this thirst for an open instruction set architecture. They would not be bound by Intel or ARM. They wanted to have an open one that they could build their own. They looked around, they found ours, and they liked it. So once we found out about that idea, we thought that would be really cool and tried to make it happen. So what's different? It's free and open. So that is, anyone can use it, and what I think is going to happen, if anyone can use it and they're all using the same thing, there's going to be more competition and I think more innovation. It's really for both the cloud and the edge, which we think are the future of computing. Little devices that on your phone's on the edge and the big cloud that has all the computings in it. So 32-bit and 64-bit. Secure, trustworthy, and it's design your own core. You can get, if you can do it yourself, you know what's in it. People are worried these days about what's in things they get from other countries. And if you were to use an open version, you can see what it's like and know what's in there. It really is a lot simpler and more elegant, in my view. You know, they got to start 25 years later, learn from all the mistakes of the first generation RISC architectures, like the ones Hennessy and I worked on. It's really simple. It's really actually pretty close to RISC-1. It's remarkably simple. It has extensions that you can add to it that are optional, which is kind of a different idea. And you can add custom instructions to do things like the domain-specific architectures that we talked about. And a big difference is this community design. There's a foundation that owns that instruction set architecture, not some company, and they're going to evolve it via these extensions. So how many how many companies are involved? We started this in 2015. It's up and to the right. There's nearly 200 today. Mentioning a couple of them, NVIDIA has announced that every single GPU will have a RISC-V microcontroller, so that's tens of millions per year. And then Western Digital is going to put processing near the data in the disk drive, so that'll be billions of RISC-V processors every year. One thing that's different about this is when you do instruction set architecture, people complain when you do a new thing in it. And so because it's open, we can bring the people who would complain into the committee and advise us, and we can get the feedback before we finalize it. So there's several committees going on that are involved in the instruction set. There's a little bit, actually, I think what I need to do here is go forward, see if that works. There's also one from NVIDIA. It has an open implementation, so there's other open architectures. And then security, I think, is going to be a boon to this idea because we'll be able to, they like things that are simple and open. And it's also everybody can work on it, so it's not just limited to a few badges. And the FPGAs are going to make this easy to do. And so let me skip ahead here again. Oops. Try that. Oh, yeah, this is sequential media. So let me just wrap up here. And then I'll have time for questions. So we think, the software advances, it allows us to have the RISC ideas and these agile, the open architectures. The raising of the software interface lets us do RISC and the domain-specific architectures. And then we're having these things that are going on about open instruction set architectures and DSAs. Lots of things are going on in the marketplace. They'll tell us about that. But just wanted to say that, what John and I think, this is going to be an exceptionally exciting decade for computer architecture, because if you want things to go faster, you're going to have to innovate at that level. So that's, with that, I think I'll open up for questions. A couple of questions. First question? First question is the hard one. Here's the hand up.
What do you think new students coming into this technology and learning architecture really need to understand to go forward and essentially provide the innovations that's going to be necessary?
What do new students need? Well, get kind of a complete hardware. What's different about now, kind of in computer architecture perspective, both the industry and the technology kind of was horizontal. It was layered, and you could do really well only understanding one of those layers. That's all I need to know. I need to know from like the compiler output to the hardware and innovate a lot. In this new era of domain-specific architectures, that's no longer true. You're going to need to know the applications, the software stack, architecture, chip design. So you're going to have to learn many more layers. So it's going to be, there's great opportunities there, but you're going to have to learn a lot more. So it'll be important for students to take a variety of classes to be able to do this. So this is for people doing architecture. If you're in software, you want to make software go faster, you better learn computer architecture. Because if you sit there and wait for Intel to make a faster processor, you're sitting there for 20 years. So it's also the flip side of this, is people are going to have to learn a lot more of the stack to be able to figure out how to go faster. And we think the opportunities is co-design, the software hardware co-design, where we do that together. And I told this to my Berkeley colleagues 15 years ago, is look, we ran out of ideas with Bernard Staedtling. Everything's going to have parallel processors in it. Be ready. So I'm saying the same. That's over. The only option forward is domain-specific architectures, custom architectures. It's completely different from class. I know you don't like it. I know it's uncomfortable, but there's no other choice. So this is bad for old people, and for companies, it's really bad if you've been making a lot of money in the old era. But there's tremendous opportunity for young people and for researchers. Question.
I've seen a little bit of preliminary work on 3D chip fabrication, so making three-dimensional chips. Do you think that presents an opportunity to increase performance?
Yeah. So we need to find a successor to the so-called planar technology, and there are people excited about 3D, but we're limited by power, right? So the power we can dissipate per chip, if you're going to do something in 3D, you still have to have a power solution to it. So there's also going to be innovation opportunities and more exotic packaging. But in always these cases, what about manufacturing and testing and power for the more exotic packages and for the 3D as well? So it's not like we're not going to have another technology to replace the so-called planar transistor semiconductor, but it may be 10 years before we get something as cost-effective, as reliable and stuff to replace the semiconductor where we are today. So in this kind of decade, we think it's going to have to be architecture that's going to have to, where you innovate until we get a better technology to come along. There's nothing right around the corner that we're going to be able to just make that transition and go back to the good old days. Andrew?
Yeah, so one of the beautiful things about RISC, right, is simple instruction sets, regular formats, and what have you. Very powerful ideas, had a huge impact. It seems like the way a lot of people are dealing with this challenge in the end of Moore's Law is by adding all kinds of specialized instructions, whether they be for crypto or even in the ARM case. I was in a briefing where they were talking about this thing called scalable vector extension, which is literally hundreds of instructions being added. So I guess the question I'd like to ask is, when you look at domain-specific architectures, right, is there a hope to have simple, regular RISC-like architectures in those spaces, or is it going to be very complicated, hairy kinds of things?
Yeah. So so I think what's going on is what's interesting. The one domain I know is the machine learning stuff. So what's really interesting is there's usually a lot of legacy code, like C++ code and stuff like that, and that's going to get RISC-V is fine for that. But then the part that doing all the number crunching that's written in things like TensorFlow or PyTorch is really small. It's really not very many lines of code. It's just incredibly compute intensive. So this idea that you have a RISC architecture and then this high-level specification for this small piece of code that runs on this accelerator, it fits pretty nicely. It's like, adding floating point instructions to that. There'll be a narrow domain that it does this exceptionally well. So that's what it looks like for me. So it would be different if what we were trying to do is take, a 100 million line C program, reverse engineer it to figure out the domain and stuff like that, then those things will happen. I think, the simple instruction set with optional support of accelerators for domains still kind of feels to me like, it fits well within the RISC philosophy. And, the enthusiasm about RISC-V is it's going to be, I would say it's going to be successful. I don't know how successful it's going to be, but we're trying to keep up with it. So somehow, even though you could argue the instruction set's more complicated, somehow there's a wall that's isolating the complexity from the rest of it, so it doesn't affect the whole thing like it did in the good old days. Okay, I think what I'm going to do, given my loquaciousness, is jump to my story. So, and the reason you do this story is that a bunch of grad students think, well, you've won the Turing Award. By the way, I only won the Turing Award 6 months ago, so I'm pretty much the same person I was I haven't changed a lot in the last 6 months. But they think, well, your life has been perfect, and I have difficulties that you've never had, so of course you were successful. So let me tell you what happened. So I was the first of my family to graduate from college. My mother, who's right there, we celebrated her 90th birthday last year, but she grew up. She grew up right in Argo, Illinois. In fact, Argo High School is still there. That's where you went to school. Yeah, it's still there. And she met my dad there in high school. And he had to move away, but he couldn't leave Lucy. And so they got married right out of high school. They had me not shortly. Sorry. More than 9 months later. A full year later. So my dad was went to community college and graduated and then started at Northwestern. But then they wanted to get a house. And, housing is really expensive in Illinois. So they went to California to get a cheap house. But my dad with 4 kids and working, he kept trying to finish that degree. And the whole time I was growing up, his joke after a while was, I'll try and beat Dave. I'm the oldest one in the family before he gets his degree. That was his joke. But I actually beat him. A couple months. And but I was I wrestled in high school and wrestled in college, and I was a math major. Computers existed. I knew of them, but there was no computer science major. There was no computers at my high school. So I didn't really think much about it. Then I'm at UCLA in a math class in the last quarter of my junior year. A math class is canceled. I looked for something to take. Oh, look, a computer course would fit that slot. Okay, I'll take it. And so I took it, and I was hooked. As prehistoric as the technology was at the time, with punch cards and line printer listings and overnight feedback on your still it had computing in it. Your ideas could come alive from your head, and I was hooked. It's like playing a 30-year-old video game. People were engaged back then. You can't believe it, but it was. So the senior year, there was no undergraduate major, but I took every computer course I did. Accidental PhD student. In my senior year, I was working at my dad's company to support myself and my wife going to college, and I said casually at the end of a computer science class, boy, I'd sure rather be doing this stuff, what I did in the class, rather than working in a factory to support myself. So on his own, he went and found me a job as undergraduate, and I had no plans at that. So he put me in an office with a bunch of grad students, and so I talked to my wife and said, well, maybe I was getting a bachelor's degree, and how about a master's degree? That seems pretty cost effective. And she said, sure. And then I was in the office, and everybody's getting a PhD. So that seemed like a good idea. So I asked my manager, well, if you can do it, sure. So that sounded good. Then we had 2 kids living in married student housing and supporting them on a 20-hour-a-week salary. We were very poor, but it was okay until the grant ran out. And then I had to get a job. It took me another 3 years to get a job, so 7.5 years to PhD. The really good thing about being in the field this long, 40 years ago, 7.5 years was a long time. Now it's not so bad. But yeah, so it took a long time. But my wife, who was born in Berkeley, and loved Northern California as a kid and wanted to go back. In fact, when we went on the recruiting tour, I said, I just can't take this seriously because I think we're going to end up at Berkeley. And I told, oh, you don't understand. UCLA's belong to Berkeley. You don't go from there to there. You don't understand academia. Okay. But so I'm starting to get job offers because I'm finally going to graduate. And she says, what about Berkeley? What about Berkeley? And so she forced me as a graduate student to call the chairman of the department at UC Berkeley to find out my application. So I still remember this, and the guy I talked to was a famous mumbler, so I could barely understand him. And I said, hi, I haven't heard from Berkeley. It's the one place that I would consider, given that my other options. And she says, well, Dave, you're in the top 10, but not the top 5. And I still remember the tremendous relief that wasn't as bearing as possible. So what I found out later is he said that to anybody who called. But then he took my application out. And there was a guy, who was hiring in this area, who was visiting Southern California. So and then he dropped by and visited, and so I got an interview and a job. And then the first project I worked on was, out of control. It was the senior guy specified it, and we were going to build a whole operating system and a whole chip and architecture, and we had no research funding. Amazingly enough, I took a leave of absence and went to Digital Equipment Corporation in Boston, and it gave me kind of 3 or 4 months to figure things out. And so how do you do research in universities, and what's a good project? What can't you do at a university, and what you can? I came back and did the RISC project. And tenure was really hard for me, for the chair, the person in Mike's job, because we publish in conferences, what no other field does. Conferences are kind of wasteless papers. It's journals that count. But I had very few journals, but he was able to get me through. And after that, it went well. So then, what worked well for me? I think in America, you grew up thinking the way to be happy is to get wealthy. But those are actually 2 independent goals. I think there are unhappy, wealthy people. I don't know, presidents might be. But those are different. So why not aim for happiness? Family first. I had some time before I got there, and I realized I had to make my family first in all these decisions, because otherwise your family, because people asking you to do things, you want to say yes, and your family can end up, dead last. And you can't be happy, if you lose the family along the way. So I have 2 sons, and I did Indian guides, and I was the scout master, and I was the assistant soccer coach and stuff like that. And so when my beautiful young boys become rebellious teenagers, you were never on, Dad. Okay, Indian guides, scouts. So family first. Passion and courage. I like to think I'm a logical person, but I'm pretty clearly a passionate person. And ironically, the physical courage that comes from wrestling turned into intellectual courage. I feel it's like my personal responsibility when somebody says something publicly to stand up, no matter what the cost to me personally, and confront that. So given I'm passionate and that, one of the things we do is, I was told when I got to Berkeley, is we value positive impact, not paper. So I love that idea. So we do research projects. In baseball terms, we swing for the fences. We're not bunting for singles. If we're trying to hit a home run when we do these projects, and because in academia, strikeouts don't matter. They remember your home runs. They don't remember all the ones that didn't work. So why not swing for the fences? And then because passionate and stand up to people, one of my colleagues gave me this observation. Friends may come and go, but enemies that keep. This is actually a very old quote, but he told it to me because I think he was worried about me. And as far as I know, I made 2 real enemies in my career. The first one was kind of an appointment, and as I look back, that I was against, and I'm very happy that person's career was elsewhere, so I feel pretty good about it. The other one was during the George W. Bush administration. He put a person in charge of DARPA, a big funding agency that decided to not fund academic research like I did. And I thought this was terrible for the country, as well as, not just for my project. And so I said, hey, let's fight this guy. And then I went around to other departments, and everybody thought this guy was a vengeful guy and didn't want to do that. But Ed Lozowski and I took this guy on. And there were costs. We didn't have any DARPA funding, and there's other things, opportunities. But it turned out he was a very unpopular guy, so when I took him on, it made a lot of friends. So pick your enemies carefully, I think would be the advice. So winning as a team versus individual. I was a wrestler, which is an individual sport, but both my high school and college coaches believed that if we bonded as a team, we'd be more successful. So I just believe that in my DNA. And this is a phrase, no losers on a winning team and no winners on a losing team. As long as you're part of a winning team, no matter what role you play, you won. If you lose, it doesn't matter how good you think you did. I think I'm good at seeking out honest feedback and learning from it. If somebody doesn't like my work, I send them a paper, and they'll be frank about what they don't like, so that's good for you. Why not do that? And then, what I've learned from that in my career, another kind of warning sign that you can take away, is if somebody, I guarantee, if somebody thinks they're the smartest person in the room, run away, all right? So in my career, the guy who I didn't want to hire thinks he's the smartest person in the room, and he's not a popular guy. A president of an Ivy League college thought he was the smartest person in the room, and he was fired. The founders of Enron thought they were the smartest people in the room, and they're convicted felons. And amazingly enough, I have an unnamed ex-brother-in-law, whose brother thought he was the smartest person in the room, and he's a convicted felon. Okay? So how is this possible? They probably are smart, but if you think you're the smartest person in the room, you don't think there's any wisdom in asking other people for your ideas, right? So I think that's the fatal flaws. But in any case, so I certainly encourage you to ask people, but in any case, if you hear of somebody who thinks they're the smartest person in the room, do the opposite of whatever they do. Stay away. One big thing at a time. I still remember kind of waking up like on a bright sunny morning, and it was this like 10 years into my career, and it's like God spoke to me. It's not how many projects you start, it's how many you finish. It was like that's obvious, right? But after that, a lot of academics say yes to them until they can't get anything else done, and they don't get very many of those done. But after that, I kind of chunked what I did. I would do one big thing at a time. So when Hennessy, I did the textbook, that was the big thing I did that year. When I was president of the ACM, that was the big thing. When I helped with the Richard Tapia, so I did one big thing. And you know what? Over 40 years, if you only do one big thing a year, that still, can be dozens of things, right? So people think you're pretty productive, but, keep that in mind. And finally, I'm a natural born optimist. I think my mom is too, but I kind of came out that way. I think, especially in research, it's better to err on optimism than pessimism. I think we can do it. There's a lot of reasons to be pessimistic. Easy to be pessimistic in research, but, with optimism, you think you can overcome it. And my story is going back to when I was 16 years old. And I was dating this girl, and I screwed up my courage to ask her to be exclusive. At the time, he said going steady. And so I asked her, would you go steady with me? She had dated a lot more people, and she was only 16, and she really didn't want to go steady with anybody then. So she told me, Dave, I don't know how to say no. So as a logical person and an optimist, not a no sounded like a yes, so I said, great. And so in her mind, she thinks, oh, I'll let this guy down later. But we've been married 51 years. That's not yet. Now, when you've been married that long, people want to know the secret to the success. So this is, you are going to be the first audience that I'm going to tell the secret to be married for a long time. And it's 9 magic words. And you're going to think it's for one of the two parties, but it's actually for both. 9 magic words. So the first 3 words, I was wrong. You were right. I love you. And there's no substitutions. I was wrong, you're right, you're a jerk. No, it doesn't cut it. Those are the 9 magic words. All right, with that, I'm really all done.
Great, well, thanks, Dave. So, like I said, I had a chance to work in close proximity with Dave, sharing a cubicle for a number of years, and that was kind of every day was like that. My advice is if you get the chance to share a cubicle with Dave Patterson, you should take it. So I would put that on my list. So thanks so much for that.